Welcome to this video, and in this video we look at the electronic implementation of PID controllers. We look at the electronic implementation of PID controllers. The implementation of PID controllers is achieved using the operational amplifier network in its inverting mode. And therefore, if the operational amplifier is to be used in its inverting mode, then we have to use two stages, where the first stage is the stage that implements the typical operation of either P, PI, PD, or PID, and the second stage is just an inverting stage. We'll go through them one by one. We start with the proportional controller. We use the operational amplifier as an inverting amplifier in two stages as follows. So this is our operational amplifier network, where the first stage, we have resistor R1 on the forward path and resistor R2 on the feedback path. But in the second stage of the operational amplifier network, both the resistors on the forward and feedback paths are equal. If we are to analyze the operational amplifier network, the first one, and take the voltage here to be the voltage V2, you'd go to write the expression of the operational amplifier network as the current in this path, which is VI over R1, plus the current in this path, which is V2 over R2, is equals to 0, since no currents leave this junction, from which we can obtain V1 over R1 to be equal to negative V2 over R2, and our ratio between V2 and VI will be equal to negative R2 over R1. Similarly, we can obtain the ratio between V out and V2 to be equal to negative R over R, following the same procedure, which is equals to negative 1. So V out over V2. And the total gain, V out over VI, will be equal to negative R2 over R1 multiplied by R1 by negative 1, which is R2 over R1. And this is our V out over VI. This will be a constant which depends on the values of the resistors R1 and R2. From the description of the proportional controller, we said that U of t is proportional to the error signal, where our controller was defined by U of S over E of S is equals to Kp. If we compare this equation with that of the operational amplifier network, then we can notice then that our constant Kp will be equal to R2 over R1. And through the operational amplifier network, we are able to achieve the proportional controller with the proportional gain constant being equal to resistance R2 over R1. The second one is the PI controller. The PI controller, or the proportional plus integral controller, is defined by U of t is equals to Kpe of t plus Ki, the integral of E of t dt, from which in Laplace form, U of S will be equal to E of S into Kp plus Ki over S. And our controller is defined by U of S over E of S is equals to Kp plus Ki over S. We call this equation 3. We proceed to obtain the electronic implementation of the controller, obtain its transfer function, and compare it with equation 3, which is the mathematical description of the proportional plus integral controller. The implementation is as follows. So the first stage, we have a resistor on the forward path and a series resistor capacitor in the feedback path. At this point, or in the feedback path, we have an impedance Z, where Z is the sum of the resistor R2 plus the reactance due to capacitor 1 over SC, which can be written as SC R2 plus 1 over SC. Then the transfer function V out over V1 will be equal to Z over R1, which is equals to, considering that this stage will implement the operation and this stage achieve sign inversion. So ideally, V2 over V1 should be negative Z over R1. But because this has a -1 transfer function or gain, then the overall gain will be Z over R1, which will be equal to SC R2 plus 1 over SC R1. Which we can write as, we split this into two terms as R2 over R1 plus 1 over SC R1. And this is our V out over V1. We call this equation 4. If we compare equation 4 and 3, where equation 3 was Kp plus 1, that is Ki over S, you notice then our Kp will be R2 over R1, and Ki will be 1 over C R1. And through this operational amplifier network, we are able to implement the proportional plus integral controller with the proportional constant or proportional gain constant being equal to R2 over R1 and the integral gain constant being equal to 1 over C R1. Next, we look at the PD or proportional plus derivative controller. The PD is defined by U of t is Kp E of t plus Kd d dt of E of t, partially proportional and partially a derivative of the error signal, from which you can write our U of S to be equal to E of S into Kp plus S Kd. And our controller will be defined by U of S over E of S is equals to Kp plus S Kd. We call this equation 5. The electronic implementation of the PD controller is achieved as follows. So on the first operational amplifier network, we have a resistor capacitor parallel network on the forward path. And a resistor on the feedback path. Then the sign inversion stage. So this is the input and this is the output. So on the forward path, we can have an impedance Z. On the forward path, we have an impedance Z. Z defined by parallel capacitor resistor network of R1 multiplied by 1 over SC over R1 plus 1 over SC, which will be equal to R1 over SC R1 plus 1. The transfer function is obtained as VO over VI is equals to R2 over Z, which will be equal to R2 over R1 into SC R1 plus 1, which we can write as R2 over R1 plus, if we open the brackets, then SC R2. And this is our V out over VI. We can call this equation 6. If we compare equation 5 and 6, then we'll obtain our proportional gain constant to be equal to R2 over R1 and our derivative gain constant to be equal to C R2. And therefore, using this operational amplifier network, we are able to implement a PD controller or a proportional plus derivative controller with the proportional gain constant being equal to R2 over R1 and the derivative gain constant being equal to C R2. Lastly, we look at the PID controller defined by U of t is equals to Kp E of t plus Ki, the integral of E of t dt plus Kd ddt of E of t. In Laplace form, we obtain U of s is equals to E of s into Kp plus Ki over s plus s Kd. And our controller will be defined by U of s over Es is equals to Kp plus Ki over s plus s Kd. And we can call this equation 7. The electronic implementation of the PID controller is achieved by combining the PI and PD as follows. On the forward path, we have a resistor capacitor parallel network. And on the feedback path, we have a resistor capacitor series network. Then the sine inverter part of the operational amplifier network. So this is our input VI, our output VO, resistor R1, capacitor C1, resistor R2, capacitor C2, and then RR. From these, we can determine the impedance on the forward path as Z1 and the impedance on the feedback path as Z2. Z1 is the resistor capacitor parallel network, giving us R1 1 over S1 over R1 plus 1 over S1, which will be equal to R1 over SC1 R1 plus 1. Z2 is the series combination of the resistor R2 and capacitance C2. So we obtain this as R2 plus 1 over SC2, which will be equal to SC2 R2 plus 1 over SC2. The gain of the operational amplifier network, V out over VI, will be equal to Z2 over Z1, which will be equal to Z2 is SC2 R2 plus 1 divided by SC2 multiplied by, we are dividing by Z1, we multiply by the reciprocal of Z1, which is SC1 R1 plus 1 over R1, which we can write as the common LCM of SC2 R1, multiply this to get S squared C1 C2 R1 R2 plus S into C2 R2 plus C1 R1 plus 1. We can break this down into 3 parts, and we start with the constant term. So we start with the term that has S into C2 R2 plus C1 R1 over SC2 R1 as follows. We write these as C1 R1 plus C2 R2 over C2 R1 plus the term that will have 1 over S. This is 1 over SC2 R1 plus the S squared term over SC2R1 will give us S C1 R2. So C2 and R1 will cancel out, and we can call this equation 8. We proceed to compare equation 7. Equation 7, allow me to rewrite equation 7. Equation 7 is Kp plus Ki over S plus SKD. This is our equation 7. Then equation 8 is obtained as C1R1 plus C2R2 over C2R1 plus 1 over SC2R1 plus SC1R2 SC1R2. This is our equation 8. So if we compare the constant term, then we'd have Kp will be equal to C1R1 plus C2R2 divided by C2R1. Our Ki will be equal to, so we compare the terms that has 1 over S, and the constant Ki will be equal to 1 over C2R1. And finally, Kd, we compare the term that has S, and our Kd will be equal to C1R2. And using the operational amplifier network given, we are able to implement the PID controller with the constants Kp, Ki, and Kd given as demonstrated in these 3 equations. And that is the implementation of PID controllers using the operational amplifier network in their inverting mode, using 2 stages of the operational amplifier network, where the first stage achieves the typical PID operation, while the second stage does the sign inversion. Otherwise, that is the end of my presentation, and thank you for watching this video.